Here we're looking at example 3 from our 2.4, number 2 set of notes. We're told that an 18 centimeter fuse is lit. And then 5 seconds after that fuse, it is going to be half of its original length. Now, if we're assuming that the fuse is burning at a steady rate, we're asked to write a linear model for the length of this fuse. So right now, if we have had 0 time that has lapsed, the length of that fuse would be 18 centimeters. So if we just imagine for a second, here is this fuse. Since 0 time has lapsed, we have 18 centimeters for this fuse. Now, 5 seconds after the fuse is being lit, so we have this thing now being lit, it is basically half of that original length. So at 5 seconds, we are half of this fuse. Well, before it was 18, so half of 18 comes out to be 9. The length of the fuse at 5 seconds is only 9. And from this, then we have 2 points. So then we can go ahead and find the rate at which this fuse is being decreased. So in other words, how much is this fuse going down by? Now, if you go ahead and find the slope, we have m is equal to, we'll call this one x1, y1. And this one x2, y2. Well, going ahead and substituting our variables in for our slope formula, we end up with 9 minus 18 all over 5 minus 0. So it looks like our slope, or rate of change, just comes out to be negative 9 over 5 centimeters. And this is centimeters per second. Now we can go ahead and construct the equation of the line. It doesn't really matter which point we choose. Typically we go with a number that has like a 0 in it, or a point that has a 0 in it. So we'll go ahead and choose this guy. So using point slope, we have y minus y1 is equal to m times x minus x1. And again, we're trying to construct a linear model that represents the length of this fuse. So going ahead and substituting our variables in, again, 0 would act as an x1, 18 would act as our y1. When we go ahead and throw this in the point slope formula, we end up then with y minus 18 is equal to our m, which is negative 9 fifths, times x minus our x1 is 0. Going ahead and distributing in our negative 9 halves, we end up with y minus 18 is equal to negative 9 fifths x. When you multiply it by 0, it would just kind of cancel out and become 0. Lastly, we're just going to add 18 to both sides. So we end up then with y is equal to negative 9 fifths x plus 18. And so here would be our linear model representing this fuse and it being lit. Again, that is example 3 from our 2.4, number 2 set of notes.